Hi. Today I'm going to revisit some of the extra practice for Chapter 2. As you have noticed that in our Quiz 2, we actually did not meet our exact progress. So I require the TA to pick several exercises for you to do the practice. So instead of reviewing the question in quiz 2, I'm going to review those exercises. So this is question 1 for the chapter 2 extra practices. The question asked us that there are V1, V2, V3, and P vectors. And A matrix is a vector obtained by collecting V1, V2, and V3. And question A asked, how many vectors are in the collections of V1, V2, and V3? So basically, this question asks us about how many vectors are in the collections of V1, V2, and V3. So this notation just means the collection of V1, V2, and V3. So there are simply 3 vectors by counting 1, 2, and 3. And question B, how many vectors are in the column space of A? And this notation representing column space of A. So we need to review what is the column space of A. So here is the definition. The column space of matrix A, denoted as COLA, is the collection of all linear combinations of the columns of A. Alternatively, column space of A will be the same with span of the columns of A. Here the lowercase a1 to an are the n columns of this A matrix. So how many vectors are in the column space of A? Since it collects all possible linear combinations, all the linear combinations are contained in the column space of A. So there should be many linear combinations. And to answer this many vectors, we should put this infinity. Means that there are infinitely many numbers of vectors in the column space of A. And for question C, is the given vector P in the column space of A? Why or why not? So in order to answer these questions, it is to determine whether vector P is in the column space of A. We can try to compute the solution of AX equals to P. Remember that A is a matrix defined as the collection of V1, V2, and V3. And if such a system AX equals to P has a solution, either it has unique solution or infinitely many solutions, then we can conclude that this vector P is in the column space of A. Otherwise means that if the system has no solution, then we conclude that P is not in the column space of A. And there was a similar example in the lecture slides for the question C. This example was collected from the lecture slides. This question asked, A is a 3x3 matrix and B is a vector. Determine whether B is in the column space of A. So this example is similar to this question C, because the question C asks exactly the same question, whether this vector P is in the column space of A. So in this example, the solution was the vector B is a linear combination of the columns of A if and only if B can be written as A times X for some X. And that is B is a linear combination of columns of A if and only if the equation AX equals to B has a solution. So in order to answer the question C, we use the same logic. We compute the linear system AX equals to P. If X exists, then we will know that P is in the column space of A. So in order to compute the linear system, I form a augmented matrix. So this is my augmented matrix. This part is my A matrix, and this is my P vector. I put them side by side and make it a augmented matrix. In order to solve for a possible solution of X, I use the Gaussian elimination and then reduce it until a echelon form. This is a echelon form. And this echelon form is equivalent to the homogeneous systems that can be expressed in this bracket. So we can find that variable x2 has a relationship with x3 through this equation. So x2 can be written as something times x3 plus a constant. And for x1, it equals to, again, x3 times some number and then plus some constant. Eventually, we find out that this is a consistent system. There are multiple solutions. So the answer for C is yes. And to answer the second half of the questions, we should say the P is in the column space of A because the linear system AX equals to P has at least one solution. And the above Gaussian eliminations requires you have a computation by hand. But this one was computed through a online calculator. You can click on this link, and then that will lead you to a online matrix calculator. And then you can choose the system of equations calculator, and that will compute the solutions of X for us. Question 2. Let V1, V2 be these two vectors and W be this vector. Determine if W is in the subspace generated by V1 and V2. Basically, subspace generated by vectors, it means the span of these two vectors. So the question is asking us if vector W is in span of V1 and V2. We can try to solve for the solution of V1 x1 plus V2 x2 equals to W, where W is now put in the right hand side of this linear system. And now I collect V1, V2, this is V1, and then V2, and W, and make it an augmented matrix. And then I perform the Gaussian elimination until I reach an echelon form. So this one is the echelon form. Okay, and then this echelon form equals to these two homogeneous equations, and that means x2 equals to 2 and x1 equals to 1. So I identify a unique solution for this linear system. So the answer for the question is yes, W is in the subspace generated by V1 and V2. Question 3. The vector x is in a subspace H with a basis B. And this basis B contains two vectors, B1 and B2. Find the B coordinate vector of x. So we need to review what is a B coordinate vector. Before that, we should review what is a basis. The basis for a subspace H is a linearly independent set in this subspace H, and also it spans the subspace H. So it has two properties. Both need to be satisfied, linearly independent, and it spans the subspace. What is the B coordinate? Such a B corresponds to a given basis. Suppose I have a capital B here. It collects B1 to BP, P vectors. This capital B is a basis for a subspace H. And for each vector x in the subspace H, we say the coordinates of x related to the basis B are the weights C1 to Cp, such that x vector can be expressed as C1 times B1. Here B1 is the basis vector, plus Cp times Bp. Bp is the last basis vector. And C1 to Cp are weights, and they are scalars. We collect C1 and Cp, P scalars together, and then this vector is called the coordinate vector of x related to B, or make it short, it's called B coordinate vector of x. So the question asks us to find the B coordinate vector of x, meaning that the question wants us to find the weight C1 and C2. The weight C1 and C2, such that this x vector can be expressed. So I have this x vector can be expressed by C1 times B1, which is 2 minus 4, plus C2 times minus 1, 5. Okay, so this is x, this is B1, this is B2. And there will be a unique value of C1 and C2 such that this equation holds. And my collection of B coordinate vector of x will be equal to the vector collecting C1 and C2. Right, and the computations can be made in below. Okay, and here C1 and C2 equals to 1 and 2. C1 and C2 equals to 1 and 2. And we can do the justification. 2 plus 1 times 2 plus 2 times minus 1 equals to 0. Okay, and then 1 times minus 3 plus 2 times 5 equals to 7. So that's a correct answer. And for the second part, the x is 1, 9. This is x equals to C1 times B1. B1 is 1 minus 5. This is B1 plus C2 times minus 2 and 3. This is B2. And again, the B coordinate vector of x is equal to the collection of C1 and C2. So the answer shows that C1 and C2 equals to -3 and -2. And we can double check -3 and -2. So this is -3 plus -2 times -2 plus 4. So that's equal to 1. And then -3 times -5 equals to 15. Plus -2 times 3. That is -6. So I have 9. So again, the solution is correct. So I have the B coordinate vector of x being -3 and -2. These two. This is the B coordinate vector of x. So the solution was right here. We need to answer this one and this one to fulfill the requirement of these questions. And here lists that there was actually a similar example in the lecture slides. So for the preparations of midterm exam, for example, you can review this example. And this question says that it's a three-dimensional problem. I have V1 and V2 given here. And the basis, capital B, includes V1 and V2. So this basis contains two vectors. And in the end of this example, we are asked to find the coordinate vector of x related to B, where x is given right here. So it's exactly the same as what we performed before, but right now we have a three-dimensional vector. So I have C1 times V1, and V1 is the first basis vector. V2 is the second basis vector. C1 times V1 plus C2 times V2 equals to x. This is x. And then eventually I compute C1 equals to 2 and C2 equals to 3. And thus the coordinate vector of x related to B, or B coordinate vector of x, is 2, 3. This is my coordinate vector of x related to B. Okay, now we're done with the question 3. For question 4, find the basis for the subspace spanned by the given vector. What is the dimension of the subspace? So even though it's not directly mentioned, we can let these four vectors be a matrix A. Let matrix A collect the given four vectors as its four columns. Then the question basically asks us, what is the dimension of the column space of A, right? It asked, what is the dimension of the subspace spanned by the given vectors? And by definition of column space was defined as the span of the column vectors. And what about the dimension of the column space of A? Here we can review that the rank of matrix A is the dimension of the column space of A. Basically, that's the definition of a rank. So in order to find the dimension of the column space of A, it's equal to find the rank of A. How do we find the rank of A? Here's the continued review. Since the pivot columns of A form a basis for column space of A, the rank of A is just the number of pivot columns in A. In other words, in order to determine the rank of A, we can count the number of pivots during the process of Gaussian elimination. So here's the process of Gaussian elimination. We start with this 4x4 matrix because we have these 4 vectors given, and then by collecting them as a matrix A equals to, A equals to a matrix, 4x4 matrix, such that the 4 columns are these 4 vectors. And then, and then we perform a Gaussian elimination. That is to reduce the original matrix to a echelon form. And then during the process, we can identify 3 pivot columns. That is, we use A to do the row replace, 1 to do the row replacement. And then we pick 5 as my second pivot to continue the row operations. My third row operations, my third pivot was chosen at this position. So I have 1, 2, 3 pivot positions. So since there are 3 pivot columns in A matrix, the rank of A equals to 3. And that is dimension of the subspace equals to 3. Here the subspace correspond to the subspace mentioned here, subspace spanned by the given vectors. Next questions. Solve the equation Ax equals to B by using the LU factorization given for A. So A matrix is given. This is A matrix given to us. B vector is also given to us. In order to solve Ax equals to B, we can use Gaussian elimination directly. But if the LU factorization was given, that is, A matrix equals to the multiplication of 2 triangular matrix. One is a lower triangular matrix, we call it L. The other is an upper triangular matrix, we call it U. Then we can review that we can solve Ax equals to B in an alternative way, which is to solve a pair of equations, 2 linear systems. We first solve for Ly equals to B, and then we get the solution of y. We put y as the right-hand side of my second linear system, that is ux equals to y. So and then eventually solve for x. And that will save us some time and numbers of operations. So here's the solution process. We first solve for Ly equals to B. In order to solve for Ly equals to B, we form an augmented matrix by putting L matrix right here, and then B vector here, and then do the row operations, and until a reduced echelon form. So y equals to 0, minus 5, minus 18. And then solve for ux equals to y. We put U matrix right here, and then y vector right here. This is my second augmented matrix. And then I continue with the Gaussian elimination until I find a reduced echelon form. So x equals to minus 5, 1, and 3. And that's my final answer. For question 6, now we have an A matrix, and this A matrix echelon form is given to us. Find basis for column space of A and non-space of A, and then state the dimensions of these subspaces. So before we start, we need to clarify these questions. There are 4 things that we need to find. The first thing is a basis for column space of A. The second thing is a basis for non-space of A. The third thing is dimension of column space of A. And the fourth thing is dimension of non-space of A. So before start computing, I have some preliminary analysis. Let's have some plan first. Like, how are we going to solve for this question? So for the first question, basis for column space of A, it equals to pivot columns of A. Pivot columns of A. So how do we identify pivot columns? This echelon form was given to us. So from this echelon form, I know that the pivot columns are 1, 2, and 4, basically, because the pivots are 5, 5, 5, these 3 positions. And then after identifying 1, 3, and 4 columns, I need to go back to the original matrix and then select the first column, the third column, and the fourth column. Then these 4 column vectors will become a basis for column space of A. And that's for question 1. So let's skip the second one temporarily and then try to solve for dimension of column space of A. What's the dimension of column space of A? It's equal to rank of A. Okay, and yeah, so it equals to rank of A. And for the second questions, basis for null space of A. Basically, we need to derive the parametric vector form and see an example below. Parametric vector form. This is the keyword. And then we derive the parametric vector form in the process of deriving a reduced echelon form. So we need to further reduce to a reduced echelon form in order to, this one was the echelon form. Don't mistaken me. This one given was the echelon form. And we need some additional processes in order to make it a reduced echelon form. And after we obtain a reduced echelon form, we can find out what is a parametric vector form. And for the parametric vector form, those vectors are automatically the basis vector for null space of A. That's for the second questions. Later we're going to see the example. And for the fourth question, dimension of null space of A, we can directly count the number of vectors in the basis because we have derived the second questions, the basis for null space of A. So we just count like how many vectors are collected in the basis for null space of A. Alternatively, we can use the rank nullity theorem to determine the dimension of null space of A. So we're going to review these processes one by one. So the first one is finding basis for a column space of A. We see that the pivot columns of matrix A form a basis for the column space of A. Notice that it is just one basis, not the unique basis, like meaning that there are many bases, but choosing pivot columns of a matrix A will be one of the bases. And then a warning, we cannot use the columns in the echelon form, but then after identifying the pivot position, we need to go back to the original matrix and then choose the original column vectors as the basis vectors, just as what we did here. We identified that the pivot positions are in first column, third column, fourth column, but we cannot pick the first column, third column, fourth column in the echelon form. We need to go back to the original matrix and pick the first column, third column, fourth column of the original matrix. So that's this warning about. How do we find a basis for non-space of A? We briefly mentioned about parametric vector form, and then also we mentioned about the reduced echelon form. We say that we need to continue our row operations in order to bring the echelon form to a reduced echelon form. And this example shows the detailed process of it. So suppose we have we have a given matrix A, and after obtaining such a form, we can write it as the simultaneous equations. Then after reordering, we find out that x1, x3 are related to other variables, but x2, x4, and x5 are free variables. And how are we going to handle that? We write the parametric vector form in this way. First, we put x1, x2, x3, x4, x5 together as a vector. And then we try to express variables in its relationship if possible. What do I mean by possibility? Because x2, x4, and x5 are free variables. There are no additional relationship between these variables and others. So I can only put x2, x4, x5 right here in my second derivation. But for x1 and x3, I have a relationship with other two variables. So instead of x1, I put 2x2 plus x4 minus 3x5. And for x3, I put minus 2 times x4 plus 2 times x2. So basically, I'm almost done with the parametric vector form. And in my third derivation, I try to separate the numerical values with variables. That is x2, x3, and x5 are put outside. And then I leave only the numerical values inside the vectors. So that becomes 2, 1, 0, 0, 0 times x2 plus 1, 0, minus 2, 1, 0 times x4 plus minus 3, 0, 2, 0, 1 times x5, separating the values and variables. So through these three processes, the first step is to equate variables if possible. If it's impossible, then you directly put free variable equals to itself. And for a second derivation, we separate the variables with numerical values. Okay, and we're done with the parametric vector form. This one is the parametric vector form. And these three vectors will become what we were going to find is the basis for non-space of A. The A matrix was given here. And the basis for non-space of A, we have identified these three vectors. So yeah, that was an example in the lecture slide. And for rank theorem, this is for the determination of dimension of non-space. If A matrix has n columns, when we know rank A plus dimension of nullity equals to n, and that's the rank theorem. Alright, so back to our question right now, question 6. The basis for column space of A. Since the echelon form was given, then it's enough to see that columns 1, 3, and 4 of original matrix A form a basis for column space of A. And the dimension of column space of A by counting the number in the basis, number of vectors in the basis is 1, 2, 3. For the basis of non-space of A, we use the reduced echelon form That is, we continue to reduce this part. We make the pivot position all 1, like here, 1, 1, 1. And then all the numbers below and above the pivots are 0. So above 1 needs to be reduced to 0. And before reducing the echelon form, all the values below pivots are already 0. But we further need to make the numbers above pivots be 0. So that leads to this homogeneous system where x2 is the free variables. Then again, I have the 3 steps derivations following the same procedure I mentioned in the example. In the first step, we try to express the variables if possible. That is, x3 equals to 0, I can put it here. x4 equals to 0. They are not free variables. They are constant, basically. And x2 is free variable, so that x2 equals to itself. x1 has a relationship with x2, so I can put it as minus 3 times x2. And for the second step, I separate the variables with numerical values. So I put the variables are x2, I put it outside, and then multiply by a vector that contains only values minus 3, 1, 0, 0. So this vectors, minus 3, 1, 0, 0, will be the only basis vector for a known space of A. And the known space of A has a dimension. Okay, dimension of known space of A equals to 1. And we can check whether the rank theorem is correct. Rank theorem says that if a matrix has four columns, how many columns do I have? Okay, four columns. 1, 2, 3, 4. 4 columns. N is number of columns. The rank theorem says that the rank of A plus dimension of known space of A should be equal to number of columns. So what is rank of A? It's equal to number of pivots, so that's 3, plus the dimension of known space of A. Here we have found out dimension of known space of A equals to 1. So 3 plus 1 equals to 4. So that's the number of columns for this matrix.